Well, in this screencast, I show several examples of integration by parts. The first few are a little bit unconventional. So if you didn't see the other screencast that does the theory and a few conventional examples, you want to do that. But here I'll show a couple of unconventional examples and then how to do definite integrals with this process. So we're already up to example 3. And in example 3, we ask for the integral of ln of x. And I know what you're thinking. You're thinking the formula says integral of u dv is uv minus integral v du. But there's no u dv thing here. Au contraire. Let that be u and let that be dv. If u is ln of x, its derivative is easy to find. And if dv is dx, then the antiderivative here is just x. So we give this a try. The integral of ln x dx is uv minus the integral of v du. Oh, is that easier to deal with? I think so. The antiderivative of 1 is x. And so we can use integration by parts to find the integral of ln of x dx. What if it gets a little more complicated? It's a general rule of thumb that we take the derivative of the thing whose derivative gets simpler, right? Like this would normally be our u because it's a polynomial, except that I don't know the antiderivative of this really easily, and I don't want to go back to that slide to find it. So what I'm going to do in this case is I'm going to let this be u, and I'm going to let the rest of it be dv. As long as the product of u and dv is everything you see, we can break this up however we like. So what's du? The derivative of ln x. What's v? Well, v is the antiderivative of this function here. Well, that doesn't look good. Let's see what this does. The formula says integral of u dv is uv minus integral of v du. So in this case, the integral of u dv is uv minus the integral of v du. Well, is that easier to deal with than what we had before? You betcha. Antiderivative here is just 1/4 x squared. And we got it. So what happens with that? This has easy derivatives and easy antiderivatives. This has easy derivatives and easy antiderivatives. So how do we go at it? Well, we just pick. I'm going to pick e to the x to be u, and I'm going to pick sine x dx to be v, and we're just going to pick a horse and ride and see what happens. So we try by formula. The integral of u dv is uv minus the integral of v du. So the integral of u dv is uv minus the integral of v du. That's a minus v du. So we ask ourselves, is that easier to deal with than what we had before? And that answer is no. This is an exponential times a trig function. This is an exponential times a trig function that's roughly the same, but we're no worse off than we were before. So the thought is, well, let's just try again. Let's let u be e to the x, and let's let dv be the trig function this time. Sorry, remaining the trig function. The trig function remains the dv, otherwise you undo what you just did. And we see where this goes. So what's this? The integral of e to the x sine x dx is negative e to the x cosine x plus uv minus the integral of v du. Well, I don't know what to do with that. That seems a little weird, doesn't it? It's like we ended up right back where we started. And that's kind of the point. We end up back where we started. This is the thing that we're looking for. This is the thing that we're looking for. So if we bring that over to the left side, two integrals of e to the x sine x dx is this. So when we're looking for 1 e to the x sine x dx, that's half as much as what you see. It's half of this plus some arbitrary constant. That's about as complicated as it'll get. I promised that I would do a definite integral. Nothing complicated about the process. We just remember that we're evaluating a definite integral. And when we're evaluating a definite integral, we run through the process. It's an integration by parts. There's your u, there's your dv. And what do? Well, the integral of u dv is uv minus the integral of v du. So the integral from 0 to pi over 2 of x cosine x dx is uv evaluated between 0 and pi over 2 minus the integral from 0 to pi over 2 of v du. So just bringing everybody all together, what's the antiderivative here? That's a plus cosine x. And we evaluate between 0 and pi over 2. Substitute the pi over 2, substitute the pi over 2, substitute the 0, substitute the 0, and you get pi over 2 minus 1. Definite integrals work the same as indefinite integrals. We just remember, as we do with fundamental theorem of calculus, to substitute, substitute, and subtract. All right. Hope this has been helpful. See you soon.